Awesome. Yeah, so hi everyone. Welcome to the Multimodal Weekly webinar series hosted by 12 Labs. For those of you who are new, we're in early stage AI startup focusing on building multimodal foundation models for video understanding. This is our initiatives to foster community discussion around research happening in this exciting space. We've been meeting on a weekly basis. Pretty much, every Friday over the past year and a half or so. Here are some of the topics that we tend to cover on a weekly basis. So news research in multimodal AI and foundation models, interesting application of multimodal in different verticals. We have a pretty good active Discord community, Discord with active engagement from members. So occasionally we have community members come in and share a variety of projects, videos that they talk. Chris, who's currently in the call, has actually been presenting several times on just different projects that he's working on. And finally, internal talks from our team members showcasing tutorials and guides using our platform and API. I've been focusing a lot on the research side of things over the past several weeks, bringing in a bunch of speakers, right? Focus on different aspects of research, from long form video understanding to video retrieval, video captioning, specific aspect of video processing, evaluation benchmark for multimodal, etc. And the speaker for this week is pretty much also really focused on video processing as a domain. The second speaker, Junhook, unfortunately couldn't make it today. He emailed me a couple hours ago, said that he's not feeling well. So we're only going to have two presentations from Dr. Minghan and then Cheng, also wrote by Rex, and they both going to focus on video segmentation. So Minghan will give a talk about her work on UniVS, Unified and Universal Video Segmentation with prompts as query, and then Rex will also focus on video segmentation, but with more focus on the object level reasoning. Yeah, so pretty coincidental that both these stuff focus on this task, but yeah, I think it's really exciting to hear different perspective on how we tackle this problem. With that, just some quick note on the logistic. Attendees, feel free to send your question on Zoom chat, and then I'll surface them to the speaker. Since there's a pretty small group, we can just have a nice Q&A with each other after each session finish. Yeah, so with that, I'll stop sharing the screen, and Minghan, you want to go ahead and share the screen and go ahead with your presentation.
Okay, thank you. The introduction from the Jenny. Yeah, let me share my screen first. Can you see my screen?
Yep, I see it.
Yeah, hello everyone. Thank you so much for having me here today. My name is Minghan Li, and you can call me Nikki. And now I'm a postdoc research fellow in the Harvard Medical School. But the paper, the talk is about the video segmentation, and it is published in my PhD period in the Hong Kong Polytechnic University. And also I'm an intern at that time is in the company Oppo. So the research is about that unified and universal video segmentation with prompts as queries. Yeah, I want to give some background about segmentation. Actually, segmentation can be divided into category-guided segmentation and prompt-guided segmentation. The category-guided segmentation is the commonly used segmentation. It includes semantic, instance, and panoptic segmentation, where the category names need to be predefined. For example, people, sky, and sea in here. In contrast, the prompt-guided segmentation includes reference segmentation and interactive segmentation, where the prompts can be language or visual prompts. For example, the text prompts can be that object descriptions like women in right, that means it's the women in the bounding box. For the interactive segmentation, the visual prompts can be points, box, or masks. In video domain, same as the image segmentation, it can also be divided into category-guided segmentation and prompt-guided segmentation. In the category-guided segmentation includes the video instance segmentation, video semantic, and video panoptic segmentation. In short, is VS, VSS, and VPS. In there, the category name need to be predefined, like the cat, person, and skateboard. For the prompt-guided segmentation, is a little different with image segmentation. In there, for example, for VOS, video object segmentation, the user can give the visual prompt in the first frame, and our model need to predict the target in the following frame. And for the panoptic VOS, that means the user can provide any visual prompts in the first frame, seen as staff class. For example, the wall in here, yeah, is more general, it's extended from the VOS. Graphing VOS, in there, the prompt is the object description. For example, a frog is holding by the person's hand. And compared to image segmentation, video segmentation focuses on the temporal consistency. For example, our model needs to predict the object along with the time. And so it is important for the temporal consistency. In the past years, the researchers proposed a lot of methods wanted to accommodate many video segmentation tasks together into a same architecture. For example, Video K-Night unifies all three video segmentation tasks in category video segmentation, and UniRefer unifies the prompt-guided segmentation. And in the TarVS and UniNext handle more video segmentation tasks. However, there no one model can accommodate all video segmentation tasks into the same architecture. That means if we wanted to process different video segmentation in we have to design different models. So in this paper, we wanted to propose the method. The name is UniVS. It can process all 6 video segmentation. So it's our motivation. Actually, there has some challenges. The challenges lies in that there has some conflicts between the video segmentation task because the video segmentation task has different problem definition and product types. For example, for the category specified segmentation, the commonly used method is that we need to detect all possible objects in each frame or in a short video clip, and then to associate objects across the time. And in there, the first detection and then segmentation. So, but for prompt-guided segmentation for VOS, PVOS, and reference VOS, the pipeline is different. For example, the user will give some text or visual prompts, and then we will to convert the prompts into the feature space. And the goal is to find the targets in the following frame. And so the tracking is very important. The model needs to accurately tracking the target in the whole video. And usually they will to update the predict mask, and it will be used in the following frame. So tracking is more important. So to address the issues and to merge the conflicts, we proposed the methods, and the name is UniVS. It's a unified and universal video segmentation. We use prompts as cores. There are three main contributions. For example, we follow the prompt to get the pipeline, and the tracking is important. So for the text or video prompts, we extract the features, and then the first contribution is that the prompt as cores. We average the prompt features stored in the memory pool, and there's a memory pool in the first frame, and then as the initial core. That means we can to explicitly decode mask, and it is explicit decoding precise. And then we can to input the initial core in the mask decoder and to predict the object mask. Actually, there are several blocks in the mask decoder, and our model maybe conflicts or cannot distinguish which one is the targets. So we propose our second contribution. We introduce a target-wise prompt cross-attention layer in the mask decoder. That means we have a cross-attention, and the core is the initial core, but the KN value is the information from the historic information in the memory pool. And in each block, in the mask decoder can learn more information from the historical information. And after that, for the prompt get segmentation, our pipeline can handle them. How about the category get segmentation? There are no any prompts, no any types of video prompts. So we propose a very simple but effective module in our strategy. We design a pseudo-mask generation. Is easier to understand. For example, we just need to, in the first frame, we detect all possible objects in the first frame, and then we view the predicted mask in the first frame as the pseudo video prompts into here in the memory pool. So in the following frame, our model needs just to repeat the prompt to get segmentation. So the framework is simple but elegant and effective. So there is the prompt as core, and there is convert video segmentation into prompt to get the segmentation. So UniVS is the first that can handle all 6 video segmentation tasks. There is the overall training framework, and there are 3 main modular: image encoder, prompt encoder, and unified video mask decoder. The image encoder converts the raw video frame into the multi-scale features, and then the features will be into the prompt encoder. For example, for video prompts, we use video sample. We sample some pixels in the video area as the prompt tokens. For the text prompts, we use the frozen clip text encoder, and we also propose a language to image cross-attention layer to map the embedding from the language space to the visual space. So, and then we got the prompt tokens. We just need to do main operation, and then it will be our view. It will be input as our initial cores. Finally, we just need to input the multi-scale mask features and our initial cores here to do unified video mask decoder. Different with the other papers, we also use the learnable core, or we use the learnable core, and we also use our proposed initial core. It is designed for the prompt-guided segmentation. So there is the output learnable mask will detect all possible objects, and prompt mask is guided by the prompts given by the user. There is the detailed about our unified video mask decoder is adapted from the mask transformer. And there is our new proposed prompt aware cross attention, and it can utilize more historical information from the memory pool. For the inference, we adopt the streaming inference. And for the prompt get segmentation, same as our training process, we just need to propose the first frame based on the video or text prompts and update the predict mask in the memory pool and just repeat. And then it's a streaming inference. For the category get video segmentation in the first frame, we have to do detection and to detect all possible objects as the pseudo video prompts, and then follow the prompt to get the segmentation to predict masks. In there, actually, if the video is very long, there may be some newly appeared objects. Actually, in our code, we will do the detection with some interval frames, for example, 100 frames or 300 frames. Yep, repeat. There are 3 training stages. The first stage is the image level training, and second is short video frame training. In there, each video clip has 3 frames. At the last, we also use the long-term fine-tuning because the long-term consistency is very important for video segmentation. And we also use almost all video segmentation data to train our model. Yep. There are no more details here. If you are interested in there, please to refer to our paper. And we also do ablation studies that shows that each component proposed in our method can bring a higher performance or stronger generalization. For example, the VS to P can make sure our model have stronger generalization. And I wanted to share an interesting visualization in here. And the first line is there is the first frame, and there is the video prompts given by the user. And there are 3 objects, car, person, and glass. Compared to the car and person and the glass is challenging and it's difficult. It's an uncommon object in COCO or the data size. And our model needs to predict the objects in the following frame. For example, here, if we without the ProCA layer, is the prompt aware cross attention layer. If we do not use the historical information from the memory pool, our model maybe cannot distinguish the glass and the person. It's reasonable. But if we use our proposed ProCA layer, and our model can performance well and can predict the mask very well. And the experimental results shows our performance with the state of the art, and we compare UniVS with the methods is individually specified for each task. For example, the VS methods is only designed for VS, and VS is only for VS. That means they can obtain a higher performance, but they have poor generalization. We also compare UniVS to the joint training or unified methods, and then we can see that UniVS is the first model that can handle all video segmentation and also obtain comparable, even state-of-the-art performance. There are some visualized results for category-guided video segmentation, and there is a video and have this thing changing here that shows that our proposed UniVS can obtain very good performance in mass. Same as the prompt get video segmentation, and in there is the video prompts given by the user in the first frame, and there's the results. same as this one and this one. And there are more visualized results here in. So for the conclusion, and UniVS is the first method to accommodate all 6 video segmentation tasks into a single framework. And there are our project page, and there show more video demos. If you are interested in our results, please scan this code. And there are our code, and it has been published in our paper. And I wanted to share more about future work that is about what video segmentation can be used in the future. Yeah, it's an interesting and open question. And I list 3. The first one is actually the tracking in UniVS is not perform not very well, but recently some tool propose data is automatic data and obtain better tracking performance. Is same too. And the last 2 is about video segmentation, because as we know that video segmentation is a semantic group or semantic clustering. So can we use the video segmentation as a semantic aware visual tokenization of multimodal large language models? Actually, there have some papers has used this idea in the image domain, not for the video domain. Actually, but video domain is more important because there has the temporal redundancy in the temporal dimension. Maybe the video segmentation can provide a higher compression ratio or something like that. Same as the video generation, yeah, but I'm not sure. I just maybe we can try if you are interested. Yeah. So this is all about my paper. Oh, thank you all of you. Any question?
Oh, thanks a lot, Minghan, for going with the presentation. Yeah, there was one brief question on Zoom chat that Vikash just brought up, but like I think he was just curious on the relationship between this and the meta SAM model, but I think you just covered in the previous slide, right?
Yeah, maybe. Okay. So, yep.
Great.
So I see this question. It's from this is maybe a basic question. How does it differ or build on top of the SAM model from Manta? Yeah, it's a good question. Very good question. Actually, this paper is motivated by the SAM. Actually, at the beginning, we wanted to do the research is about the SAM tool. We want to annotate more data using the automatic annotation flow. But you know, it's very difficult for academic academic life is engineering. So we transfer to a small research to accommodate all these segmentation together. So I think the same tool is better for the tracking because it can obtain better tracking performance and also can do prompt guided segmentation. But if you have the requirements about the category guided segmentation, maybe our methods can perform well because our UniVS support the category as the prompt. Yep. If I am understanding correctly, the inference is online. Do you think we are leaving performance on the table if we are not using? You mean that if we are not using offline, actually, yes, if we are not using offline processing, we are do have a better performance for online, but that the challenge lies in that how to design the memory pool, how to design the interaction from the memory pool. Yeah, you need to tell your model which kind of type or which target is your target, which object is your target. So I maybe in there same two some two also have the memory attention, have memory bank. Yeah.
Great.
Yeah. So
Awesome.
okay.
So in this slide, you mentioned video segmentation can be used as a semantic aware visual organization and multimodal LLMs.
Yeah.
I think you mean like you just create better embeddings, right? For video, like create better video embeddings to be used for like video language model. Is that the idea?
Yeah, yeah. If you use the video segmentation and as a video tokenization, we can sure that you will have the higher compression ratio, but we cannot sure you have the better performance. You need to pre-train your video encoder. That your video encoder is the video segmentation, and that depends on how to design the model and how to train your model and how to set up your data. Yeah.
Awesome.
Yeah.
Do you mind going back to the slide at the training process?
Okay, training precise. You mean?
Yeah, I think this one is very, very nice diagram here.
Yeah.
So the top part is image encoder, and then it's the bottom
Prompt encoder.
yeah, it's the text encoder, and within the text encoder, you like have multiple prompt query, visual prompts, text prompt.
You mean that why we use separate the video sample and clip text prompts?
Yeah, so here you
Yeah.
so you have a visual and encoder for the visual prompt, right? And then you have like
Yeah.
yeah,
Yeah,
like
this video sample, we just, for example, there had the mask video sample that, for example, we sample some points from the area in the here, for example, 8 point or 16 point here, and then the feature is from this feature map. We do not have another video encoder to get the video features. Yeah, so this is just to extract the points.
yep.
But yeah, but for the text prompts, they have the different modality. So we need to use clip text encoder to get the text embedding, and then we need to align the dimension or channel. So we use the language to image cross attention layer, and then yeah, we have the same embedding space.
Nice.
Yeah.
Yeah, I think I understand the language to image cross attention is basically like an alignment layer, right? To align language and image.
Yes, alignment.
And for the unified video mask decoder, like looks like you incorporate everything, right, into that decoder layer.
Yep, and yeah, so I think the elegance shows in the unified video mask decoder. We just introduced the prompt cross attention layer because yeah, for the learnable query, it's like the learnable query in the mask former, and then it is responsible for detect all objects. but we don't want to tracking as the post-processing step. So we use the initial query as the in there. It can, as we know that, for example, this right triangle is for the person, and then in the initial query, it has the information about the person. And after the unified video mask decoder, and the output is also responsible for the person, we just need to use in the streaming line and no need tracking.
Yeah.
Yes. Yeah.
Awesome. And then for the inference, I think you also have a slide on the inference process, right?
Let me, here.
Unified streaming inference. So are these like sequential step? Like you go with the prompt, then the prompt guided, and then the category guided?
Yep.
What I'm just curious, what is like the compute? Is it expensive, like in terms of like doing this inference online?
Yeah, actually, it's maybe it's an online inference. It's more, yeah, it is an online inference.
I see. What part of this pipeline is like most expensive?
Okay, and for example, for the prompt guided video segmentation, and the user will give you some prompts, video prompts or text prompts, and then we will put into the prompts for video prompts is only in the first in the first frame. So we will input them into the prompt encoder, and then have the initial query. And for the first frame, it will be input into image encoder, and then they will to predict the mask in the first frame. And then we need to update our memory. And for the for the following frame, and we use the masks in the memory pool as our video prompts. So we don't care is in the first frame, it can be video or text prompts, but in the following frame, it will convert into all video prompts because we have the predict mask in the first frame.
All right. Awesome. Well, thanks a lot, Minghan, for the interpretation. For the audience, if you have any further question for her, feel free to put on the Zoom chat, and then she can answer the question apply. Yeah.
Thank you so much. Thank you, all of you.
Yeah, great. So with that, yeah, Rex, do you want to go ahead and share your screen and start your presentation?
Right. Hello, everyone. And yeah, thank you for the introduction. Can you see my screen?
Yep, I can see it.
Okay, great. So hello, everyone. I'm Rex, and I'm currently a PhD candidate at UIUC. I did my undergrad and master in Hong Kong. So coincidentally, Minghan and I might both be in Hong Kong a few years ago. Today, I'll be sharing our paper, like this talk on object level reasoning in video object segmentation and its multimodal applications. Video segmentation algorithms are very useful. Like, for example, in video editing, we can use those segmentations to separate foreground from the background and to apply different effects using a segmentation mask. We can also use those algorithms for a lot of scientific or monitoring purposes. In this example, we can use them to keep track of sheep in the farm automatically. So in general, we are interested in sort of multimodal video segmentation. This is also highly related to what Minghan just talked about. But we are taking a somewhat different approach. So we are taking a decoupled approach, which is, I guess, in contrast to Minghan's end-to-end approach. Happy to discuss the pros and cons of those approaches later. So the way we do this is we do it in two steps. First, we do text to image, single image segmentation. We give the model a text prompt, in this case, just guinea pigs and chicken, and we ask the model to output a single frame segmentation. And in the second step, we do mask propagation, that propagates this single frame detection to the video level. So for text to image, we have a lot of models like Grounding Dino or Lisa. And for mass propagation, we have models like SEM, XMEM, or our paper that I'm going to present today is Cutie, which is our sort of latest addition in this direction, which is equipped with object-level reasoning. I guess the latest model in this mass propagation area will be SEM2, as we discussed earlier. And well, in terms of metrics, it does perform better than Cutie. And I guess if you read the SEM2 paper, Cutie was used extensively as the baseline to compare against. Some advantage that Cutie still has is it's trained on much less data. It's more compute manageable, and I believe it's still more efficient on most hardwares. So this is kind of a demonstration of what this decoupled pipeline can achieve. So the only input that the user has given is the guinea pigs and chicken, and it can perform this sort of segmentation. So our paper here is titled Putting the Object Back into Video Object Segmentation. This is a joint work between UIUC and Adobe, and it was presented at CBL this year as a highlight paper. We are looking at mass propagation, which is also called video object segmentation here. So we aim to track and segment objects given in an initial template as shown in the below video. Importantly, this task is class agnostic. So we put no limitations on the class of the object. And that input template can either come from a user or some other detection algorithm as shown in the previous slide. So how do we track these objects? Well, first we have the input, which is the template image and the template mask. We also have an image that we wish to segment, that is a query image. We can train an end-to-end network that take all of these as input and predict the segmentation mask, which is the target mask. And to generalize on this idea, we can rename the template image and the template mask as a unified memory bank. We can also make the observation that this query image and the target mask now form a new template pair, which we can add to the memory bank to supplement the features that is existing in the memory bank. We call this a memory formulation, which consists of mainly two steps. But first, we construct or build a memory bank using the input templates and subsequently segmented frames. And then we transfer those masks from the memory bank to the output query frame. Most of the prior work in this direction that do this memory formulation, they relies on a lot of what we call pixel level matching. That is, for each pixel in the target frame, they find the most likely match in the memory and use that to guide the segmentation process. So this would work if those objects are very distinct. So if you can find those accurate matches. But when they are similarly looking objects in the scene, so somewhere in this case, you might get wrong matches, like you may match foreground to the background or background to the foreground. And that is going to lead to inaccurate segmentation, because those inaccurate matches would guide the segmentation model to produce this broken or fragmented mask in the output, which is pretty much undesirable. However, we know that the target object should be a complete object, but we should produce some holistic segmentation. But our algorithm doesn't manage to produce those complete objects. Here, our main contribution is to correct this type of behavior. We believe that having object-level reasoning would lead to a more holistic segmentation. So how do we do that? To give an overview, there is like an architecture diagram of our method. And for more technical details, I'm always happy to take questions, or you can also refer to our paper. First, we encode that query frame and the memory bank using existing mechanisms. So this comes from prior works like XMEM. And we use that for an initial pixel level reading. So that gives us the pixel level readout. However, we do know that those pixel level readouts are rather noisy. So we introduce two additional high-level object-level representations that are the object memory and the object queries, respectively. The object memory is extracted from the memory frames using the encoder, and the object queries are learned end-to-end as some sort of embeddings. We then feed all those types of features, the high resolution pixel readout, the high level object queries, and the object memory into what we call an object transformer. So this object transformer consists of 8 different transformer blocks, which iteratively refines and denoise the pixel level readout. And finally, with that refined representation, we fit that into a decoder that gives us the final mask. And here we give you a more detailed look of what a block in the object transformer looks like. So again, I'm not going into all the details, but the important things to know here is that we have 2 cross-attention layers, which allow us to interact between the object level features and the pixel level features. So these 2 cross-attention, the first one allows the pixel level features to go into the object level features. And the second cross-attention kind of do the reverse. So we are putting those object level features back into the pixel level features. And we are also using a self-attention layer for the object features only. So this allows us to do object level reasoning, but note that we avoid doing any types of pixel to pixel attention, such as pixel level self-attention, because that would be very expensive because we have a lot of pixels that we need to work with. By not doing that, we make the entire transformer block very efficient. So how does this method perform? Our method achieves state-of-the-art performance at the time in several different datasets, and it also does this pretty efficiently. Most significantly, we get the highest improvement in the Mosaic dataset, which is the most challenging dataset here. That is, it comes with a lot of occlusion. It includes a lot of objects with similar appearance. We also do well on the DivX and UWS. And in terms of FPS, we can achieve more than 40 FPS per second, 40 FPS on 3100 GPU, and without using any of the inference tricks like mixed precision or touch.compound. And on our project page, we also provide models that are trained on even larger datasets to achieve a even better performance. We can also combine our method with long-term memory, which was proposed in XMM, and achieve state-of-the-art performance on long video datasets as well, such as bursts. Bursts typically contain more than 1,000 frames per video. Even with that, our method uses relatively little memory and can be deployed on many consumer-grade systems. So what makes our algorithm works well? We think the key here is really to make good use of both pixel level features and object level features. From this table, we can see that our algorithm achieves the best result when we use both types of features and perform worse when we only use any one of them. And here we visualize the intermediate mass predicted by our model in each layer or each block of the object transform. Going from the left to the right, we are applying more transformer blocks, and with that, more object level reasoning. And that gives us less noise in the output segmentation and a much more complete segmentation overall. And here we look at the attention maps, difference between pixel level features and object level features. As shown, the pixel level features, they give us a much broader range or coverage of attention over the target image, but then they're also easily distracted by similar objects in the scene. But if you look at object level features, although it's more sparse, but this is also much more focused on the target object. So by using both types of features, that is how we achieve a more robust segmentation. To showcase what the algorithm can do, we again look at that multimodal application. So here, the user provides a simple text prompt, capybara, and we first use a text-to-image model to detect image level segmentation. And we can feed that into Cutie to produce a video level segmentation. So this is the output of our algorithm. It's not perfect, but the user is doing little work here, just giving the names of the target object that they wish to segment. So it is relatively lightweight on the user. And this is another example where the input prompt is pick. Again, there are some errors in the scene, but it can track most of the picks very well here. And this is another application or another demo. And here we want to show a sort of video editing type of demo. So our algorithm produces a mask, but we can use that mask to do much more. For example, in this case, we use that mask to insert a layer between the foreground and the background. That gives us some sort of effect that you want to do in video editing. And here we again, we in a very different domain, we produce a segmentation mask. We apply that as a video effects. In this case, we are running a video inpainting algorithm. So if you have used those before, you know those require some input masks. And our algorithm can be used to generate those input masks. And this example is when we use segment anything as the image model. So even though that algorithm, it tried to segment everything in the scene, and we basically try to propagate all those different masks to the videos as well. So our code is available online, code demo, and interactive too, everything. So feel free to try it out and visit our website to know more. Thank you for your time, and I'll be happy to take questions.
Awesome. Yeah, thanks, Rex. I also put the two links here on the chat as well a few minutes ago. For anyone who wanna dive a bit deeper on, yeah, I think super cool interactive demo and very relevant multimodal applications that you showcased, especially on the video editing side. I think that is something that I see I'm most excited about, right? Because we do work with a lot of video editors at 12 Labs, and I think some of these techniques are really, really useful to help them do the job better. Not just text instruction, but also it looks like image instruction, image query in this scenario, right? For the audience, is there any like immediate question for us that you want to ask? If so, you just like raise your hand. I do the unmute. Okay.
I see a hand raised.
Yeah, Vikash, I just unmute you. Do you want to unmute and ask your question? And Minghan as well.
Can you hear me now?
Yep.
Yeah, it's a good paper because I know you are the author of X Memory. Yeah, it's a good paper too. Yeah, so can you go back to the architecture training?
Right.
Yeah. Yeah, this pipeline. So so for the memory frame and mask, the encoder is, for example, is a smaller network, ResNet 80.
Right.
Yeah, the encoder, for example, is ResNet 50.
Yes.
So they have the pixel memory and object memory. Actually, at the beginning, actually UniVS cannot obtain the higher performance that Cutie because we do not have the another encoder and to get the features from the spatial temporal features. So how about the memory, or how about the here? Maybe it's the storage, memory storage is huge or not?
The memory usage, I guess we show that in a table earlier as well. Thank you for the question. Like, I think it takes like several gigabytes, mainly because we are not continuously storing all the different frames in memory. Like we're only keeping, say, the most recent 5 frames, and also a set of long-term memory.
So
Yeah, we also tried a lot of object level sort of prompts or tokens, like kind of like in your paper, I guess. But we couldn't get it to work as well on video object segmentation. And the reason we believe is because like if you only go object level, we no longer have this high resolution pixel memory representation. So when we compress everything to the object level, it becomes low resolution. And that is really hard to work with in a video object segmentation setting, where the object appearance can be very different in different videos.
So another question is about that. Your ablation studies showed that the pixel memory or pixel features is more important than the object level features.
Right.
But can you move the next slide, maybe next slide, the realization about feature map? Yeah, this one. And actually, from the realization, I think the object level attention map is more important because the pixel attention map has some noise to the other, for example, other object, but the object core has yeah. But I'm not sure. I think the object level feature map is more important.
I see. So, yeah, that's a good question. First, I guess I can start with why pixel level features are more important here. I guess UIUC algorithms traditionally they has been built on only pixel level features. So in a sense, that's why they work so well. Like they have been refined a lot, and that is what people has been relying on.
Okay.
You only do object level features, as you mentioned before, it sends very low resolution, and it does not give us enough information on how to segment a target object. And yeah, back to this visualization, this might be a bit, I guess it's not exactly related to, like, say, we only use pixel level features or we only use object level features. Because this attention map is created by appending the object level features with the pixel level features.
Yeah.
So if we only do object level features, we actually cannot create this attention map.
Yeah.
So this is already based on some pixel level features.
Yeah, maybe the pixel feature map can provide some fine grain information for the mask, but the object level, it is enough. Yeah, got it. Thank you so much.
Thanks a lot. Thank you for your question.
Hi, Rex, can you hear me now?
Yes.
Yep.
Hey, I was just curious. I know you're talking about object level features, but pixel level features are given in any model, right? I mean, that's the basic layer on top of which the other abstractions are built. So I think the innovation here is, and I'm just trying to understand, it probably is not a question. So the innovation here is you're combining that object level, features and pixel level features, and that is somehow enabling you to isolate the object in a video in all the frames. And that's the value proposition here, because you just showed us some videos where when you isolate that object, you are able to provide some layer between the background and the object, where you can do a lot of things. Maybe that is your, that is how you're going to sell the model, for lack of a better word. Is my understanding correct? That's the innovation space?
Okay, let's see if I understand. So yes, this is correct that the pixel level features is basically foundational in all the different models, right?
Right.
In the video audio segmentation context, I guess if we say we do not look at the object level features, we can cross away object memory, object queries, and the object transform. then we go from pixel readout directly to the decoder. That is what actually previous work does. And that works, right? That has been the state of the art before Cutie. So, but the problem with that is that this pixel level readout is done with a single layer of attention. So it doesn't have the chance to refine a lot of the noisy features. So this object level representation here is really to allow it a chance to refine those features while still letting it be efficient, because we don't have pixel to pixel self-attention.
Gotcha. And again, just for my curiosity, did you train your model from scratch, or is it built on some open source model?
This is trained from scratch. I mean, except the encoder is probably initialized on some ImageNet pre-training, but everybody does that.
Okay, I see. Oh, and what training data set did you use? The entire internet, or how do you manage the data set?
Data set, we mainly use the open source benchmarks stuff. So DayRex, UIUC, and some image level, like image segmentation data set as well for pre-training.
I see. Thank you.
Thank you.
Awesome. So I really like the fact that you have like an interactive demo in the repo. I think that allow people to just have a more practical usage of the project, right? Which is great. So I'm curious, what's the future direction? What's next for, like, what's after Cutie? I think going back to the slide when you have like the two direction, right? Video segmentation tasks.
So what I guess we has been more recently working on is some integrations with large language models as well.
Mm-hmm.
So the ability to use more contextual prompt to segment the target object. So here we're still very much relying on some descriptive noun, so the algorithm can pick up on all those objects. And we also relied on the text to image module. And when we put the text to image module, let me go back to that slide. So when we put the text to image segmentation with mask propagation together, we actually see quite a bit of errors in the joint, like how we combine those. So that's a really hard problem. So I guess that's where end-to-end approach, like the Minghan's method, would work better in those areas because it's trained end-to-end. So yeah, having a large language model allows you to do better prompt reasoning, and also I guess having trying to make the entire architecture more end-to-end would be a good way to go. And with that, we might also be using some pre-trained models from Meta, like SEM2. We can't really train those models in universities, but we might benefit from their pre-trained rate as well.
Absolutely. Great. Yeah, I think that makes sense. So yes, again, thanks Rex for spending your time today and looking over the demo and the talks.
Thank you.
Yeah, I think we're at the top of the hour, so we can probably close up the webinar now. Thanks to the speakers for preparing information to present today, and thanks to attendees for attending. The recording of this session will be available on YouTube within the next 4 or 5 weeks. So I'll be sure to put it on the Tall Labs YouTube channels, and it's also share with the speaker as well, so they can promote it with the internal community. Once again, we run this session on a weekly basis, most usually on Friday or at this time, 1:30, 2:30 Pacific time. So yeah, if you enjoy the content and find informative, good luck to see you in the upcoming session. Yeah, so with that, I just started recording, and I hope you all have a great rest of your weekend. Thanks, everyone. Bye.